Okay, moving right along into Chapter 4, now that we've got a brief understanding of natural reactivity and writing radioactive equations, we have now the time to stop and think about how we actually measure this radioactivity and how we know that we have a radioactive element or elements present. So some of these will probably be familiar and maybe some not so familiar when we talk about these particulars of radiation measurement here in this subtopic. All right, the tried and true method that you've probably heard of or maybe even seen a representation of one of these is the Geiger counter, technically a Geiger-Muller counter, which detects beta and gamma radiation. And the way it does that is by using the ions produced by the radiation to create an electrical current. And if you're familiar with this, that's what gives rise to that characteristic beeping, is the completion of the current by those ions produced, and that's tracked as a beep. And also there's the meter that can quantify how many of those episodes of ionizing radiation are produced per unit time. Now, in addition to the Geiger-Muller counter, you also have a scintillation counter that deals with, instead of ionizing radiation completing circuit to give rise to an audible beep, you have little flashes of light to track radioactivity, but we don't go into detail there in this course on that. What we will talk about now is radiation units. So units of radiation include the Curie, obviously named after Madame Curie, one of our most famous female scientists, and we're happy to claim her as a chemist. She and her husband obviously did a lot of the seminal work on radioactivity. The Curie measures activity as the number of atoms that decay in 1 second for 1 gram of radium, the element that they spent their time on, and she did much more work than her husband Pierre when he was killed in a wagon accident. The RAD, radiation absorbed dose, measures the radiation absorbed by tissues of the body, so this is really for the biological end of things. And then also the REM, radiation equivalent, measures biological damage caused by different types of radiation. So the Curie is sort of the unit that applies to everything. RAD and REM, we're looking at specifically tissues, living tissues, and biological damage caused to living organisms. Some additional units: the becquerel is defined as 1 disintegration per second, and it's the SI unit for radioactivity. The gray is defined as the joules of energy absorbed by 1 kilogram of body tissue, and it's equal to 100 rad. And then finally the sievert is the SI unit for REM, and it's equal to 100 rem. So we won't use a whole lot of these very often. It's more important in this course that you understand the differing activities of different radioactive elements, and especially the differing biological damage that can be done by these different types of radioactive decay. So here's table 4.4 to summarize those units of radiation measurement. Measuring the activity, the number of disintegrations per unit time. We have the common unit of the Curie, the technical SI unit, the becquerel, and the relationship there is 1 Curie is equal to 3.7 times 10 to the 10th becquerels. For absorbed dose, if we're looking at a particular tissue that's been subject to radioactive decay processes, the common unit's the rad, the SI unit officially is the gray, and the relationship is that 1 gray is equal to 100 rads. And then finally, if we're looking at how much biological damage we expect to be done by a given type of radioactive decay, the common unit is the rem, the SI unit is the sievert, and the relationship, again, just like the gray and the rad, we have 1 sievert equal to 100 rem. Alright, so if radioactive decay gives rise to energetic particles or waves that can be damaging to living tissue, human tissue in particular, we tend to be concerned about, we want to think about our exposures. And so exposure to radiation happens from naturally occurring radioisotopes, including potassium-40 is a particularly important one. And there's not much we can do to stop that. It's out there in nature. There's these varying number and types of decay processes that happen as a result of just naturally occurring radioactive isotopes. There's also medical and dental procedures that involve intentionally exposing people to radioactive isotopes in order to do some imaging afterward is usually the reason for that, or to treat certain diseases. I mentioned gamma radiation being used to treat cancer by killing those cancer cells selectively. And then finally, air travel, radon, smoking cigarettes, these are other things that can cause exposures. Air travel, there's ionizing radiation, and it's relatively minor energy that we're talking about. Some people travel a lot by air. Some people travel essentially not at all by air, whether it's to limit exposure or whether they have other fears of flying. But it's generally deemed safe because you're exposed to relatively little amounts of relatively low energy radiation. Radon we talked about as being a danger if the bedrock is rich in radioactive isotopes that give rise to radon. Then you should certainly get your lowest level of your home tested and make sure that you're not exposing yourself to radon. And smoking cigarettes, of course, we all know better, but it is a difficult habit to break if you are a smoker. But certainly not only for the radiation, but for other health concerns, if at all possible, quitting smoking can be a very important step to extending quantity and quality of life. There was also a table on that previous slide. If you didn't look at it while you were listening to me, you can take a step back or just get it in the notes and see that most of those natural exposures and even the medical procedures and air travel, they all tend to be relatively small amounts. Some of the upper GI tract, that one had quite a high number, and then of course the radon exposure, that's going to vary depending on how much radon is present, but that was also a pretty large number. So radiation sickness happens generally when there's exposure that's significant. So if it's less than 25 rem, usually you can't see any symptoms of radiation sickness, and again, less than 25 rem is where most of us are on that natural exposure count. If you have a whole body exposure of 1 sievert, there's probably a temporary decrease in the number of white blood cells, and when you're no longer exposed and the white blood cells can replicate and replace those missing white blood cells, then things should go back to normal. If you have exposure to radiation greater than 1 sievert, then you can have what's known as radiation sickness, and that's much more severe and generally requires medical treatment. So the radiation sickness can vary in intensity depending on how much of the body is exposed and what levels you're exposed to. The LD50, the lethal dose for half the population, is the amount of radiation to the whole body that would kill half the population. If we're talking about humans or lab rats or whatever we might be talking about, that will vary. And for people, if you get a whole body radiation of 6 sievert or greater, that's going to be fatal for about half of the population within a few weeks. And you can see the LD50 for various types of life, lethal doses of whole body for some life forms. Insects and bacteria are quite resistant. Humans, little lower than rats and a little higher than dogs. So I guess that's where we are on the food chain there in terms of lethal doses of whole body radiation. And again, it tends not to be instantly fatal unless you're dealing with really large doses of something like gamma radiation. But oftentimes it's because of the radiation sickness, the later death of cells due to that exposure. So try to limit your exposures, and certainly limit your exposures to less than 500 rem, and certainly, with food and environmental exposures and even air travel, we tend to be well under 100 rem for the most part. All right, so before we leave this interesting subchapter topic of measuring radiation, let's see how you're doing with understanding the different units of radiation. So this question, this learning check, asks which unit of radiation measurement measures biological damage. Is it A, the rad, B, the Becquerel, C, the rem, or D, activity? So pause the video if you haven't already made your selection, and we'll see how you did. Alright, so hopefully you correctly selected C, the rem. That's the one there that is in particular interested with biological damage. So hopefully you've had a good exposure, no pun intended there, to our radioactive radiation measurement sub-chapter topic. And again, we're not going to deal a whole lot with solving mathematical questions about this. It's just more for your understanding to realize that, of course, radioactive decay can be damaging to living tissue, and we need some way to quantify it in order to determine what the expected outcome is. Is it something temporary, like a decrease in white blood cell count, or is it something that's likely to be fatal in a matter of weeks? So on that happy note, why don't we go ahead and close this 4.3, and we'll see you for 4.4, the next part of Chapter 4, in the next video.